CPAP. All right, so we'll get started today. The first thing is to get the adder 4 out of the way because I said when you turn in homework assignments, I'll give you at least the solution, the key, how it's done. So we'll work with that. Then we'll start up Logisim just in time for the other topic that we'll go over today. So we'll be talking about the control unit of a processor today. It is being recorded. Let me just double check on it. Yep, it is being recorded. Yesterday I was I typed up the entire command before the lab time in cisp310, and at the end of the entire lab session, I realized I forgot to press the enter key. So it has happened the first time in this semester I forgot to press the enter key after entering the entire command. Fortunately, most students actually stayed during that lab time, so it was actually not too big of a deal for people who stayed. All right, so here's your homework assignment. Let me sign in first, and then we'll go ahead and get started with the homework assignment. Oops. No. Use the right password. And this is all in data and number representation. Okay. And this is your homework assignment. All right, so I'll follow my own instruction, to get this done. And the first thing is to start up Logisim. So we'll go ahead and I'm gonna use a command line to start it. So Java -jar Logisim. So alrighty. So here we have Logisim. Are you guys okay? Do you have any questions?
It's a Logisim.
Yeah, it's a Logisim.
Oh, can you get it started?
Well,
Okay.
no. So then the question is just basically, well, you'll probably end up answering it.
Okay, so I'm gonna answer the question. Hopefully, with the rest of today's session. So name the design adder 4. This is the file name you should use to save the file. So that's the first thing I mentioned. So that should be the first thing that should be done. Is just to click File, Save, and call it adder 4. The extension is automatic, so you don't have to worry about the extension. And that's the first thing to do. Okay. So I'm hoping you guys are not too eager to get into the actual logic design and skip the first part. Leave it as I'll just leave it as untitled. That's all right. Second thing: use and, or, and not gates. Use pins, and use the label of pins to remember which one is which one. Use nested design. Design a component, then use it in another component. Make a half adder first, then make a full adder from half adders, and any necessary additional components, which is a hint because you need a disjunction to connect the output carry of both half adders. In the main design area, use multiple full adders. So that's basically the structure of your design. The final design has the following I/O pins. Use the label property of a pin to label it. Use the text label to label pins of a component. So I'll show you guys what I mean by that. 4 input pins designated A3 to A0 for the 4 bits of the first number. 4 input pins designated B3 to B0 for the 4 bits of the second number. 4 output pins, I use D because it's a difference, from the subtractor, but it's okay, it will still be okay. 1 output pin designated as C as the final, carry, borrow bit, it's the last one. Design a half adder first and test it. If it works, turn it into a component, blah, 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 blah. Okay, so here we have the actual equations, and this is a repetition of what you have seen already, so this is nothing new. So we'll go ahead and start with this. Now the way we start with this is the result is the exclusive OR of the inputs, and then the carry is the conjunction of the input. Okay. So are there any questions at this point about all of this stuff? No questions? Okay. Yep. Go ahead.
That's subtraction of the.
Which one?
This one.
This table?
I think so.
This table is for
Down there.
addition.
It says subtraction.
But he has like subtraction through both of them.
Oh, okay, right. Okay. Oh, you mean this part here? It's actually the definition of binary addition.
Yeah.
I was.
Grading part later.
Mhm.
Yeah, and your grading part only has subtraction, but it's.
Yeah, the grading criteria, I'm gonna change it. That's that's not it. Yep.
Did I say 0 plus 1 has 1 carry? Oh, wait, never mind. Never mind.
Okay. All right. So we'll go ahead and put some gates and pins together and get this done. All right. So we'll go to gates first. We'll need a simple AND gate just for the carry. So I'll go ahead and make it a narrow one. Limit the inputs to only 2. And then for the exclusive OR, because the homework assignment, call for AND, OR, and NOT gates only. Okay, so we'll go ahead and use just AND, OR, and NOT gates. Now, how do you do it with just AND, OR, and NOT gate? Do you guys still remember that?
Yeah.
Okay, so A exclusive OR B is the same thing as, well, either way, not A and B, and then the whole thing, or not A and not B. Okay, so when you look at this equation, you can turn it into gates. And remember last time I kind of showed you guys how to do it. You just look at the structure of the expressions. So the OR is the last one, and then what you're ORing is the conjunction of certain components. So you have a conjunction here, and then on one side of the conjunction you have a NOT gate and an A here, and then the other one is just B. This one is just the reverse. You have A, and then you have the negation and a B. Okay, so B, these two go to the same pin, input pin. These two A's will go to the same pin. So that's basically looking at the gates kind of sideways. Okay, if you tilt your head, counterclockwise 90 degrees, that would be kind of like the structure of those gates for exclusive OR. So we'll go ahead and implement all of these gates here. We'll pull some gates. If you use a conjunction gate and just use the negation of the input, that's fine. Okay, that's not a problem. So you can certainly do that if you want to save one NOT gate. I'm just going to use all individual gates in this case, just so that it looks a little bit busy. Okay, it's not a big deal. Not going to be. And so here's a NOT gate, and I can replicate a NOT gate like that. And then we also need 2 AND gates. So we'll drag and drop. Oh, we have one that's already in the right form, so we duplicate and duplicate. So we have 2 of these. Oops. And then come on, I just want 1. There we go. And then we have a single OR gate. So we can also use this one here, which is about the same. We change the number of bits to 2. And I always want to change the gate size to narrow, so it doesn't use up as much space on screen. We'll handle the exclusive OR first. And oh, by the way, we also need some pins, so we'll go ahead and get some pins here. So we have 1 input pin, 2 input pins, and then we'll have 2 output pins as well. The 2 output pins are the carry pin, which is coming from here, and the result pin, which is going to be here. But since these are all output pins, you change the output from no to yes, because no is the default. So you change it both to yes, and then you can also change the facing. So if you change the facing before you duplicate it, that saves you a little bit of time. Okay. Yep.
If you select the item on the screen and use the arrow keys on the keyboard, it rotates for you.
Oh, okay. Thanks. That's good to know. Intuitive. Okay, so this is the carry output, and this is the result output, and it's just a matter of making the connections, and it doesn't have to look nice. Okay, you can see that mine just doesn't. It's not looking very nice. I mean, it's not very symmetric. So as far as I'm concerned, as long as it is functional, it's going to be okay. And we'll make this input pin all the way here. That goes straight into one of these, and we'll need 1 tap here, 1 tap all the way here, and then with this guy we need 1 tap here and 1 tap all the way here. Okay, so that looks about right. And then the other thing you can also do is to turn off tri-state. You don't have to, but if you turn off tri-state, it makes it easier to test the design. So you just have to turn it off. And I think if you pick this one, it's by default you're having the tri-state turned off. All right, so now we have a half adder, and before I go on and turn this into a component, I better test this first, just to make sure that this is actually working before I use it as a component. It also helps if you label it, but the labeling does not show in the component view. Okay, so the labeling only works when you are looking into the exploded view of the inside of the component. So, but that's okay. I will still put it here.
If you hover your mouse over where
right, it shows when you hover, but it doesn't show when you drag it. So, this is our carry output, and this is our result. And we can also change the label location to east, just so that it looks a little bit nicer. Definitely not required. Okay. So now it's time to test it. When you test this, there are exactly 4 possible input combinations. Being AB, 0, 0, 0, 1, 1, 0, and 1, 1. Those are the 4 possible input combinations. So you just have to make sure that it does work for all possible cases. So we'll start with 0, 0. So according to this picture right now, 0 plus 0 has a result of 0 and a carry of 0. That's correct. 0 plus 1. 0 plus 1 has a result of 1 and it has a carry of 0. That is correct as well. 1 plus 1 has a carry of 1 but a result of 0. That's correct. And the last one is 1 plus 0 has a result of 1 and a carry of 0. So it does work in all 4 cases in this case. So my half adder is now done. Okay, it's time to turn it into a component. And according to Tristan, there are many ways to do this. So one way to do it is to right-click this guy and then change it.
Oh, you just click on it and go to circuit name down below.
Change. Oh, okay, I see. Change the circuit name to half adder. So I just use a HA for half adder. And you can also change. Well, you can change quite a few things. But now I just change it into half adder, and you can create a new main.
By clicking the little plus further up.
Little plus.
Green plus.
Oh, right here. Okay. So now we can add the main circuit back on, or we can just add a full adder. So I'm going to add full adder in this case. And if you click on half adder, you should see the tool to turn it into a component. So this is the component view of a half adder. Doesn't look right to me. There we go. I just double-clicked the other one and double-click on this one. So now it is time to label the input and the outputs. So for this one, if you click on it, it shows you where it is in the original circuit. Let me do that one more time. Oh, did it before.
If you just click a different one.
Oh, I need to click a different one. There we go. So you can see at the lower right-hand corner, it shows you what pin this is corresponding to in the exploded view of the actual component. So this is a quick and easy way for you to find out, okay, how should I label this port here? This is A, this is B, this is our result, and this is our carry. So we'll go ahead and just use all that, or use the same labels, and it's just using a label like this one. This is A, which is the input, and this is B, which is the other input. This is our carry, and this is our result. I just do it like this, and then I use the other tool to move the components into the right place. It doesn't have to look really nice, as long as I can tell which pin is which pin, it's going to be okay. Yep.
If I not label this, is that okay?
Sorry?
If I not label this at all, is that okay? You didn't actually specifically say label this. You only asked us to label the last one.
Well, it helps you, when you're designing your design.
Didn't do it.
Yeah.
Okay.
Yeah, it's kind of like commenting in in programming, it's really going to be just be helping you while you're working on it. Okay, so now I have the half adder, labeled. I can now use it to create the full adder. So, I need 2 of these. So here's one, here's the other one. And I also need a disjunction because I need to connect the carry output of both of those into one single output. So I'll use a OR gate, which is right here. And make sure that this OR gate only has 2 inputs. And make it smaller, like that. And then I need a bunch of pins. Okay, how many pins do I need for a full adder?
5.
5. Yep, 5 pins. We need 5 pins. We have 1 carry in, 1 carry out, 2 bits to add as the input, and then the result of the adding. So there are 5 pins to a full adder. All right, so let's go ahead and pick out those pins. We'll just go out and pick out 3 of these input pins. Okay, so we have 3 input pins and 2 output pins. So we'll put the output pins over here, like so. And now it's time to make all the connections. 2 of the input pins, which are representing the input or the bits that you're actually adding, those will be labeled. I'll just go ahead and label one B and the other one A, because they are representing bits that you're adding. So this part is not necessary because it won't even show up in the component view, but it is helpful for me. Okay, so this one is the carry input, so I call it C in, and then this one I'll designate this one as carry out, C out, and I'll designate this one as the result, which is the sum of the 2 bits after a full adding column. Are there any questions at this point about having all these components on the screen first? No questions? Okay. If there are no questions, it's time to make connections, right? So the connections, for the first half adder is pretty easy. It's just A going to A and B going to B, because that is just really just using the input pins to create the result that will go into the second half adder. So now we have the result of the first half adder connecting to one of the pins of the second half adder. It doesn't really matter which one because adding is commutative, so it doesn't really matter. When you're dealing with a subtractor, then you have to be careful. So we have it like this, okay? And this is also kind of reflecting the same order as what I usually do on the board, okay? So if you use this particular order, making a 4-bit subtractor is actually easier, because otherwise you might have to change the positions of the inputs to make it work for a subtractor. All right, so now we have the result. This result is easy. It just goes all the way to the final result of the full adder, like that. And then the 2 carries have to be combined to the output of carry output. So they go, each one individually will go into the disjunction or the OR gate, like so. And then the output of the OR gate connects to the carry output, like that. So now we can test it. Okay, we have 8 possible input, and we will go ahead and test a few of those, because it's going to get a little bit boring to test all 8. Okay, so we'll test some of the more interesting ones. And it is already testing the case where all the inputs are 0. In other words, when carry in is 0, there's no carry from the previous digit, the previous column. And I'm adding 0 to 0, the output is 0. And there's a carry of 0 as an output. That makes perfect sense. If I make any one of these 3 a 1, the output is a 1, and there's no the carry out is also a 0. So if I just make it a 1, you can see that's happening just the way it's supposed to. If I make 2 of the inputs 1s, then the carry output should be a 1, and the result should be a 0. Doesn't matter which 2. So these 2, okay, and these 2, and then we have these 2. Same end result. Do we have any questions about this part? So the only one left is the last one, where we have 1, 1, 1. Okay. So when all three inputs are all ones, then we have a result of 1 and also a carry of 1. That's the output. So we'll go ahead and test that one final case, like so, and it does work out for all 8 cases. So we are done testing a full adder. In this case, it's time to turn it into a component. So to turn it into a component, you just click on this guy here, and look at the component view, and then we'll just go ahead and label these guys. Now, if you don't like this picture because all the pins are kind of like squeezed together and it's not easy to read, you can certainly change it if you want to. So for those of you who decide, hey, this is not looking right, you can go ahead and make a larger component out of it. Okay, so just drag the rectangle, and the pins can also be dragged. So you can just drag the pins so that they space out a little bit more, leaving you more space to put some comments on the components. That's the, I think that's the dragger.
Yeah, it calls it the anchor. Okay.
Yeah.
I don't know what that means.
The anchor means when you rotate the part, it's rotating around that.
Oh,
Yeah. All right.
right.
All right. So this is our A. So I'm going to label all of these. So we'll have A, B, C in. This is C out. Now, C out and C in, the way I put it here, doesn't make it very easy to make connections. So if you want to make it nicer, you can definitely do something about it. But I'm just going to make it so that it does work, and that's all. So we have A, B, C in. Okay, so now we have a full adder. So once the full adder is done, it is time to make the main portion, which is our 4-bit adder. Okay. And there are 2 ways to do it. If you want to use a half adder as the on the first column, you can certainly do that. If you want a full adder, you can do that too. But on the other hand, if you use a full adder, you have to use a 0 to feed into the C in. Okay. So that's the only one little caveat if you want to use a full adder for all 4 columns. So we'll go ahead and do this part here. This is once again our main part, and we'll go ahead and pick out 4 full adders. Okay, so 1, 2, and then from 2 we can make 4. There we go. Sorry?
No, I'm saying the reason why I was telling them, I changed my shape because I didn't like all the pins being on the same side, because now you can make some really fancy.
Yeah, you can do rotations too. If you do a rotation, I think it looks a little bit nicer. It's still, not gonna be right because if you want it to be stackable, the way to make it stackable is to have C in on this side, C in on the other side, and result here, and then the 2 inputs coming through there. That makes it very stackable because you can just kind of keep stacking it. Okay. Well, as long as it gets the job done, it's okay. This is not a routing class. If this were a routing class for PCBs, what I just did would get a really bad grade because it's functional. It will get a C. Okay, according to my own grading scheme, that's gonna get a C because it is correct, but it's just barely meeting the minimum because it is definitely not route friendly. Whereas this is really route friendly. All right. So now we have there are several ways to do this. Okay, I'm gonna take out these guys, after making them, because I can make all the pins first, and then I can replicate the parts. That makes it a little bit easier. So we'll go ahead and pick out some pins. Okay. So we need 2 input pins, and use the cursor key to rotate. Okay, there we go. Oh, nice. Okay, that worked. And 2 input pins for A and B. So we'll go ahead and gonna make one up and one down, just so that this way it's easier to see which one is which one. And we'll make it like that. So this is A and this is B. C in is really on the wrong side, so this is gonna look ugly. And then the output pin is here. I want it to face up, and we'll go ahead and connect the result to the output pin. There we go. C in and C out are really on the opposite side, of what I really want them to be. I can, quote unquote, fix this problem by making the least significant bit all the way on the left-hand side, but that would be like totally against convention. So I would much rather, butcher the design here. I don't think there's a way to make a mirror image out of it at this point. So what I'll do is I'm going to replicate this 4 times. So duplicate to make a second one. I think at this point you guys know what to do, but I'm just gonna finish this anyway. Like that. And then the rest is really just a whole bunch of making connections. Okay, the first thing I would do is to label these guys. So I'm gonna label this one as A0, and then this one's going to be A1, A2, and the other one is A3. And then this one will be B3. This is going to be B2, B1, and B0. And then this one also needs an extra, output pin. So we need an extra output pin of the carry itself. So we'll go ahead and pick out an output pin, and we'll make it face that way. And I'm just gonna stick it up here. Oh, ugly. The ironic part is I actually do PCB layout. All right, so we got almost everything here. This carry in has to be a 0 because there are no less significant bits before bit 0. So this one needs to get a 0. So for those of you who did it this way, you have to go find a 0, and I think it's under wiring. Constant?
Right there, under
Right under clock.
It looks like a 1.
There we go. And we can change it to a 0, like so. And we'll just make a connection here. All right, so now the rest is really just connecting the output of the carry from one to the other one. Yeah, it's lucky. As I said, I would not get a very good score if this is a routing project, There we go. Yeah, well, it's okay. I'm missing one last part. Okay, the output pins are not labeled, so I'm gonna label those guys too. This is our D0, and here's D1, D2, and D3. There we go. Okay, so now we got the whole thing done, I think. Any questions? So we'll go ahead and test it a little bit. Pick some, useful, test cases. Now it is actually emulating or simulating right now. It's adding 0 to 0. So if you add 0 to 0, you get 0, and then the extra carry. Oh, I forgot to label this guy. So we'll label it. There we go. Okay. So the extra carry is also a 0. Now, if I change these pins, if anyone want to be able to enter multiple bits at the same time, you can define a multi-bit pin and then use the bus, the splitter, to split it into 4 different pins or different wires, and each wire goes into one of the inputs. So you can certainly make it kind of look nicer if you want to. I'll demonstrate that later on because we have a lot of that stuff in the control unit of a processor. So we'll certainly have a demonstration of that. But for now, let's just go ahead and add 1 and 1. Okay, so if you add 1 and 1, the output is 0, 0, 1, 0, and then there's no extra carry at the end, which is correct. If you are adding 1, 1, 1, 1 to just 1, the output is 0, 0, 0, 0 with an extra carry, which is correct. Okay, so you can play with this a little bit more if you want to, but since I tested each individual whole adder, correct, I verified it worked correctly, so I'm pretty sure this is all working just fine. Yep, questions?
That right, what you actually just did, that's an actual overflow?
We
It's
don't
like the
call it an
same
overflow. We just say that the 4-bit number cannot store the value of basically 15 plus 1.
So there's like a particular instance that like makes it an overflow, not just any chance, not just a carry bit.
Overflow is a specific name for a condition that we have not talked about yet. Overflow is applicable when you're dealing with signed numbers. So when we're dealing with unsigned numbers, we don't use the term overflow, but I know what you mean. It's running out of bits to represent the value that it needs to store. All right. So are there any other questions about the 4-bit adder? Okay. Now, if I just turn in the file in the file system right now, I'll be getting a very low score, if anything, right? Because I did not save it. I saved it once when I changed the name, when the whole thing was empty, and I don't think I have saved it ever again. So I'm hoping nobody made that mistake, work out the whole thing and did not save it, and then go to the file system and say, okay, I just need to turn in this file. I mean, sometimes people do that. So I'll just go ahead and save it now, and now I can turn in the file that is already saved and it has the design. Are there any questions? Yep.
I missed you made that constant 0 on that one.
Uh-huh.
How did you do that?
It's under the constants, which is this one here. So you drag one of these things over, and you can turn it into, okay, this is number of bits. You can turn this into a 0 or 1. Now you can avoid using a constant altogether. If the first bit, if you use a half adder for the first column, that means you don't need to use a 0.
I spent like half an hour trying to figure it out. Just to get better.
Okay. All right. So are we kind of okay with this homework assignment? Okay. So if this is okay, we'll go ahead and start with something that is also involving a lot of logic sim, but I think it's a lot more fun. It's a lot more fun because we are now looking into the processor, but using logic sim to give us an idea of what it looks like. The von Neumann machine topic, where we talked about the memory cycles, like how to read from memory, how to write to memory. I'm not going to give you any homework assignments for that one, just because I showed you the whole sequence already. If I asked you, okay, what steps do you need to take to write a particular content to a location in memory, you just have to replay watch the YouTube, and then you just do it. Just follow the steps. Okay, so it's not going to be very useful testing that one. But the control unit is kind of fun. So when we click on control unit, I moved the files around a little bit, so you might not see this earlier because I just moved it. This one is interesting in a way because it is actually a processor, okay? But it's a processor made out of very simple components, so you can actually see level by level, how all the different components are connected in the processor. It is kind of complicated in a way. If you look at the overall design, it's kind of complicated. But if you look at each individual component and kind of drill down to the lowest level first, then it gives you a kind of more systematic way of looking at a processor. So we'll go ahead and take a look at this file. This is just a zip file. You can download it and then unzip it. Oh, that's not what I want to do. That is not what I want to do. I just want to save. Click on the wrong link. Okay, so it's just a regular zip file. You can download it and unzip it in Windows. And I'm going to go to my command prompt here and do it on the command line. So I'm gonna make a new folder, text processor. Oh, it's already there. It probably has the same design already. Let me just check the dates. Yeah, that's probably already the same design. So I'm gonna remove text processor and then just unzip the folder so that this way I work with the same file that you'll be working on when you download it from Moodle. All right. So when you look at the folder or when you look at the content of the folder, it has a few files. It has a circuit file, cisp310, which is a logic sim file. Okay, that one actually contains the full design. And it has a ODS document, which is an open document spreadsheet file. Okay, that one shows you something that is interesting, but we probably will not get to that one today. But if you're curious about what it is, you can definitely open it up and see what it is. MCC.ROM is the microcode ROM. Okay, this is the magic of everything. Okay, this is where we give the processor the ability to execute instructions. So MCC.ROM is really useful. The other one, which is LD-RAM, is an actual program that you can load into RAM so they can run the program from RAM. Okay, so that's how that's what these 4 files are for. I probably should have made a little README file to explain all that stuff, but since it's for class, I'm just going to do the explanation in class. Are there any questions at this point?
Are all of
Did you say what the .ods was again?
The ODS is a spreadsheet file. You can use LibreOffice or OpenOffice to open it. Go ahead.
yeah, other than that ODS file, the rest are viewable with the text editor? Probably not RAM.
They are probably viewable. The RAM files, I'm not sure. I have never really looked at it. Yeah, so it's really just text file, displaying the content. Yeah. Yep, go ahead.
One more time, the MCC-ROM gives the processor the ability to what?
To execute instructions. In other words, the MCC.ROM file is kind of like a program, but it's not a program from the perspective of a developer. It is a program that is it's like a sequencer. Okay, the other way to put it is it's like a sequencer. It sequences various operations so that you end up doing something meaningful in the processor. This is also a good time to talk a little bit about RISC versus CISC architecture. RISC is Reduced Instruction Set Computer, RISC, and CISC is CISC, which stands for Complex Instruction Set Computer. Okay, and those terms you can look it up on online pretty easily. Okay, just look up RISC, and the first entry to Wikipedia is the right one. Okay, so this is RISC, Reduced Instruction Set Computer or computing. Okay, depending on whether you're describing how it is done or the hardware that is actually doing it. CISC, CISC, same way. If you just look it up in Google, you will find it. And the first entry is Wikipedia, and it explains this is complex instruction set computing. So they're basically just quote-unquote opposing design philosophy in terms of the design of the processor that is inside a computer or your cell phone. Okay. Now this is really kind of nice in a way because what you have on your cell phone is a RISC processor. What you have on your desktop computer is almost certainly a CISC processor. Okay, so we can actually do a compare and contrast pretty effectively using those two as contrasting devices because one uses the one and the other one uses the other. Okay. So with complex instruction set computing, what it means is there are many instructions with this type of processor. The Intel x86 family or the Pentium line processor probably has close to 400 or 500 different instructions. Okay? And those instructions are complex in several ways. They can do a lot. One single instruction can do quite a lot of operations already. So what do you think happens to the number of transistors? Does it increase or decrease the number of transistors on the hardware itself? Increase. Yep, exactly. So when you look at an Intel processor, it has a much larger die, even though we are now down to what 18 nanometer process, but it doesn't negate the fact that you need a lot of transistors to get it done. Okay. A RISC processor, on the other hand, will only give you a very small number of instructions, and each one can only do this much. So you have to use multiple instructions in order to do the same thing as one single CISC instruction. But from the perspective of the hardware, do you think a CISC processor is larger or smaller than a RISC? The other way around,
Yeah.
sorry. So when you compare a RISC processor to a CISC processor, which one is smaller?
RISC.
A RISC processor. Okay, so let's just I'm pretty sure this is not to scale, but I'm just going to use this as an example. Okay. So let's say this is a typical i5 processor. I don't care exactly which family, which process, because the i5 is not really exactly, specifying, the process or the size of the transistor. It's kind of more of a generic consumer name of that line of processor. And I'm going to call this one a ARM processor, and I know there are multiple different ARMs, but we'll just use this diagram to say, okay, this is a typical cell phone processor, and this is a typical desktop processor. Okay. So the size are definitely different. So because of the size being different, what do you think will be the consequences? What do you think the die size, how does it change other things? Okay, so let's take a look at, go ahead.
Heat dissipation.
Heat dissipation, okay. And
Faster execution.
faster execution. So let's write down those things. So we have a power consumption, so power, heat, okay, because these two are related. Very little energy is actually spent doing computing. Most of it is dissipated as heat. So when you have a processor that has a higher power dissipation or power consumption, it actually runs hotter. Okay. And then what was the other one? Speed, right? Okay, speed. What else?
Size.
Size. Okay, size is kind of obvious. I'm going to add yield to it. Now, yield is not the same thing as efficiency or speed. Yield is it has to do with from a single wafer, okay, which is what you make processor or make processor dies out of. What would be the success rate? Okay, if I get 100 individual processors out of one single wafer, how many of those would be usable? Okay, how many will be unusable because of defects? Okay, and defect is going to happen anyway. So we'll look at all of these factors. So the first factor I'm going to look at is just going to be yield, because this is the manufacturing process. So when you look at yield, you look at a wafer which is actually about this size, 300 millimeter wide. Okay, this is a little bit, it's about right. Okay, so a real wafer is really about this size. And we'll look at two wafers, okay? The first wafer is going to have i5 processors. The second wafer is going to have ARM processors. And this is obviously very, very exaggerated, okay? So we'll just say that, with this one, we can get, like this many, i5 processors out of it. And then with this one, because it's using the ARM processors, they're much smaller, so we can get a lot more processors per wafer. So, okay, fine. So, as far as the use of material is concerned, obviously the ARM processor is going to be less expensive compared to the Intel processor, because you are just getting a whole lot more out of one wafer compared to the i5 processor. But the cost effectiveness does not stop here. Okay, this is assuming the manufacturing process does not introduce defects. But no manufacturing process is perfect. Okay, defects will happen regardless. So when you have defects, it is usually measured on a defect per square, whatever, per area. Okay. In other words, regardless of which processor you're making, the number of defects would be about the same. Okay. So we will end up with about the same number of red dots, on the wafer. But if you have one red dot on a die, that one cannot be used. Okay. assuming it is a very damaging kind of defect. So when you're dealing with ARM processor, we have 1, 2, 3, okay, let's say 4, 5, because this one kind of went across the two. Okay. So I'm just identifying all the ones that I cannot use. This is a 4 because it is right at the intersection of 4 dies. Okay. And so we end up, killing quite a few processors. But when you look at the Intel example, it's much worse, right? Because the area of each processor die is larger, so the chances of having a single defect landing on it is also larger. So in this case, we don't really have a whole lot left. Right? So in terms of the percentage of usable processors per wafer, the RISC architecture definitely wins. Go ahead.
Well, I was just wondering, like this doesn't have much to do with anything, but like, what happens with the rounded parts of the wafer?
We cannot use it. The wafer is a round thing, so all of that stuff is, I don't think they can use it. They may be able to fit like smaller designs around the round edges. In other words, if they can utilize the area better, if they put smaller dies around the edges, but then it becomes a problem when you have to cut it into the actual processor die. So I'm not really, I don't know for sure how Intel does it. Whether they try to optimize the area by putting like smaller components all the way here, or what.
Why did they use rounds wafers?
That is a good question. I think it has to do with how they make the substrate. Yeah, but I know for sure that they are all round. It probably has to do with how the wafer itself is manufactured in the first place. So probably has to do with the rotational process, and that's why it's probably a cylindrical thing to begin with, and they cut it into slices. I don't know for sure.
Yeah.
All right. So from the perspective of yield, RISC wins, hands down. Okay. Not only can you fit more per wafer, the success rate is also much higher because of the smaller area. Okay, is that okay? All right, so in terms of yield, RISC wins. Let's take a look at size. It's kind of hard to say because whether it's a bigger or smaller, is it really better? We don't know. But speed, we can speak to it, right? Let's take a look at speed. Remember what I said about cisp? Each instruction can do more. Whereas with RISC, you have to combine multiple instructions to do what a single cisp instruction can do. Okay, so needless to say, okay, everything else being the same clock speed, or same everything else, cisp is going to be a little bit faster. Okay, just because you don't have to go back to memory all the time and say, okay, what is the next instruction? What is the next instruction, and so on. So what this means is if you want to have a certain number of mils, okay, million instructions per second, okay, or effectively you'll do a particular type of calculation, chances are if you use a cisp processor, it's faster, okay, on a per processor basis. Yep.
Before like the supercomputers, were they then mostly be cisp processors? For like high.
That's a good question. I'll address that question because speed per processor is only one part of that equation. Okay, because that equation is actually pretty complicated. Because of this. Okay, in terms of power and heat problems. Okay, this is a big one. When you look at power and heat dissipation, a cisp design is going to run hotter just because there are more transistors, right? But it's not just because it has more transistors. It's also because it's not using the transistors effectively. Okay, that means when you look at the i5 processor, when you execute whatever instruction, there's a lot of stuff going on. Okay, which is not really just the adder circuit, but there's a lot of other stuff that also has to be changing state and consuming power. So basically, in the end, when you look at power and heat and you combine it with speed, what the unit what people look at is MIPS, MIPS, million instructions per second per watt. In other words, or per joules, if you will, okay? J is actually the more appropriate term, per unit of energy instead of per unit of power. Okay, for those of you who are taking physics, you can tell the difference, but they're basically the same thing. So when you look at how much computation is done per unit of energy, as it turns out, cisc is losing out to RISC in this case. So even though one single cisc processor per clock can do more compared to a RISC processor per clock, when you look at the actual amount of energy consumed to, let's say, recalculate a spreadsheet or to do a fractal graphics or to do whatever, okay? As it turns out, even though the RISC processor is going to take longer, it's actually going to consume less energy in the end. Am I doing okay so far with this? One way to look at this is to look at a rabbit versus a turtle. Okay, now a rabbit is mammalian. Okay, it has a higher body temperature. It has a much more efficient way of circulating air, intaking oxygen and stuff like that, and obviously it can run faster. Okay, a turtle, on the other hand, is reptilian. Now reptilian, are known to be very energy efficient. Okay, they're cold-blooded. Okay, they cannot even operate at a certain temperature because they cannot self-regulate. But they're very energy efficient. So if you go, if you look at, okay, here's a rabbit, it's a turtle, and they're going to carry the same payload. Okay, and I want both of those to end up at that wall. The rabbit will get there first, and then the turtle will take his time and end up there much later. But when you look at the amount of calorie consumed by the two animals, the rabbit will be consuming a lot more to get there with the payload compared to the turtle. Are we doing okay so far with this analogy? Okay. So why do you care? I mean, we just want to get there. Why do we care whether it is energy efficient or not? Well, okay, so let's take a look at something else, okay? Something that is at a much more macro scale instead of a micro scale. Let's look at data centers. Like computation centers, that Google would use. So how much processing power do you think Google wants?
As much as they can get.
As much as they can get. Okay, very good. Okay, so they don't have a, go ahead.
No, I don't have to say that.
Yeah, and in fact, if you don't know, I will tell you, Google is actually licensed as an energy provider. As a company, it is now licensed. They can, if they want to, compete with SMUN and Pacific PG&E. Okay. Do you know why? Because it doesn't want to buy power. It's consuming so much power with its own data centers. It's saying, okay, I want to be able to generate my own power and not have to buy it from PG&E. Okay. And obviously, it depends on whether it's more cost-effective one way or another, but it wants to have that option. Okay, so if PG&E starts to charge Google a lot of money for the power it consumed, Google says, you know what? I'm just going to cut this line here and have my own power plant. Okay, so that's the limitation. Okay, but that's not really the limitation, because when you look at power, we can produce a lot of power using power plants and whatnot. The limiting factor is, okay, I'm not going to say it, I'll give you a scenario so that you guys can remember it really well. How many of you have LAN parties occasionally? Maybe not so occasionally, regularly. Okay. So when you have a LAN party, how many people do you usually invite?
I usually have like 10 people.
10 people, okay, so let's say it's 10 people, okay? So let's say you have 10 people, and what kind of facility, where do you do the LAN party? At a house, in a house? Okay, so you have a house, you get 10 people, and they all bring their souped up gaming computers. Okay, let's take a look at the equations. You have 10 people, and let's say each person brings along a computer that needs a 1 kilowatt power supply and close to using all 1 kilowatt when you're playing games. So the end result is you're using 10 kilowatts of power. Now that's really quite a bit of power. Okay, your hair dryer is only 1.2 kilowatt. Okay. Okay, and then you try to stick those 10 people into a living room, let's say. Okay, and what is the usual size of a living room that you can use to figure out?
About this size. About 2/3 of.
Give me a square
100
footage.
square foot.
20 by 20.
20 by 20?
Yeah, so
120 that sounds about right. Okay, so you have this much power, and you have 20 by 20, 20 feet by 20 feet. Okay, which gives you 400 square feet, which is about right. Okay.
But usually like 8 bucks.
Okay. Now, have you ever done this in the summer? You cannot do this in the summer. Okay. Now let's think about why that is the case. Okay. First of all, your breaker is gonna pop. Okay, because I don't think okay, most circuit breakers has a limit of how many amps? 15 or 30, depending on whether it's a good size or a small size. You're dealing with 10 kilowatt here, and at 100 volt, how many amps are we drawing? 100 amps. Are we starting to understand the math here? Okay, 10,000 watts, okay? And the voltage is 110, so let's round it down to 100 volts. So that gives you 100 amps. Is that right? 4 zeros, right? Okay, so 100 amps will need 4 30 amp circuits. So just in terms of power distribution, you have a little bit of an issue already. Because most of the time in the same living room, they're all connected to either one or at the most 2 30 amp circuits. So you'll be popping those circuits left and right. And people will be screaming. It's like, oh, my game just got ruined. Okay, but that's not even the worst of your problem. Let's say you have diesel generators running outside and in the power using extension cords. Okay, and you need pretty good extension cords so that the extension cord itself does not melt. Okay, so let's say you bring extra power in. What's going to happen next? Okay, remember. It's going to get hot, exactly, because out of the 10 kilowatts, okay, very little of that is actually quote-unquote doing computation. Most, 99 point something percent of that power is converted into just plain heat, okay? 10 kilowatts converted all into heat is a lot of heat, okay? You just kind of imagine, you go to, Walmart right now, you pick up 8 of those electric heaters, turn them all on in full power at the same time in the same room, which is only 400 square feet, okay? And it adds up, right? So that's why I asked you, have you ever done it in the summer? Because you cannot do it in the summer. No air conditioning can extract that much heat effectively, within this much space. Now, if you space it out, if you go to somebody's house that is like 500 square feet, then it's a different story, because most of those houses have 2 heavy-duty AC units, and they can extract the heat, a little bit more effectively than something that is designed only for 400 square feet. Now, we are not even adding the people. Each person is at least a 200 watt, heat supply. Okay. Now, when you're gaming, you'll probably be pushing 300. So we have 3 additional kilowatts just because of the people. So you have to add 3 kilowatts because of the 10 people. Yep.
So are they not watching it either? I mean, are they using monitors?
The monitors are not really that big of a deal. Monitors tend to be about 20 to 30 watts. Yeah, so it's not really a big deal. In the grand scheme of things, it's less energy dissipated than you. A fraction of what you're dissipating. So,
like usually when I touch my monitor, it feels pretty cool. If they're using a flat screen.
Yeah, well, the flat screen, and also because now we use an LED for the backlighting, which is actually where the energy goes for the most part. LED is very efficient, and that's why with a 30 watt type of backlighting, using LED, you'll be fine.
Sorry, these computers really pull at 1 kilowatt per unit.
Oh yeah, yeah. It's mostly pulled by the graphics cards. Yeah, each graphics card can pull about 300 watts, or 2 to 300 watts, and then you have designs that can make use of 2 of those in tandem. So there
That's a
you
lot.
have 600 watts.
Crossfire.
Sorry? Oh, you can use 3 now?
Yeah, no,
Wow.
you can go quad.
Yeah, you
You can go quad.
Wow. Okay, so you can, so 1 kilowatt is not enough anymore.
Yeah, because most guys, if you're like LAN partying and your friends are all bringing 600.
So your friends would have to bring their own generator and their own AC unit, their own cooling system. You know, it has to be like a self-contained environment. We'll just call it a gaming pod. You know, and you design it to be a trailer, so your friends will all be.
That's why people use the internet.
Wow. But that gives you an idea of what we're dealing with here, okay? So Google wants even more processing power, and they want to put it all packed into a very small space. Because unlike you guys playing video games, server racks do not need desk space or space for the monitor, right? So you can stack up racks after racks and racks of computers, and each rack has multiple 1 of you or 2 of you processor units. So you're packing even more processing power per square foot. So what do you think is the limitation?
How many air conditioners you can fit on top of the building?
Heat extraction.
Yeah.
No, because it turns out heat extraction is the limitation.
So it's not like a lot of those server companies offshore their stuff. So like Google's whatever their server place is actually not in the US. It's like somewhere where it's really cold.
Yeah, but that still does not defeat the
Yeah,
the
but it
problem
helps a
of-
lot more than say it was in Arizona.
Yeah, they still need a lot of the power just for heat extraction itself. Yeah.
With that big of an obstacle that heat presents, I mean, I never hear about processors being rated to be cooler, like to use less energy or at least convert less into heat. Is that an actual field that they're pushing?
It is an actual field they're pushing because if you kind of follow what IBM is doing with their mainframe computers, they're not using Intel processors. They stopped using Intel processors a long time ago. What architecture do you think they use on those IBM mainframe computers? PowerPC. The PowerPC architecture, which is also a RISC architecture. Okay, that's actually one of the first commercial RISC architectures. Because what they found out is the MIPS per juice rating of the PowerPC is way superior to the best i5 processor, the mobile version of the i5 processor. So in order to pack more processing power where heat extraction is the limitation, they basically go for the RISC architectures. Now you're basically saying, okay, instead of using 5 rabbits, I'm using 100 turtles to do the same amount of work, because the 100 turtle to get the same job done will only take 2 pounds of feed, whereas the rabbits, on the other hand, will take 10 pounds of feed. And it is the feed that is the problem, okay? How much energy is needed to get that much work done. Yep.
Although for like that size differential, so is it like the surface area of the i5 would actually present a greater area to dissipate the heat? Is that negligible?
It does not really help because when you look at the entire die size and you compare it to the die size of an ARM, once again, if you look at square area, the area, if you look at MIPS per area, the ARM is still winning. And the area is kind of where the power consumption comes in. It's not the only thing, but that's also partially where it comes in. Now, if you guys want to really look at the numbers, we can take a look at i5 processor area. Well, i5 and i7 are about the same. They're. I just need to take a really quick. 160, okay, 160 millimeters squared. So that's about what? 160. Okay, so we'll just put it here. So that's about 13 millimeters squared, right? 13 millimeter, squared. So if you kind of imagine 1.3 centimeter squared, that's actually the quote unquote size of the die itself. And then we can look at the other processor, right? We can look at ARM, but ARM has multiple variants of that. So we'll say, sorry, ARM. So ARM processor.
Maybe if you strip
Yeah.
might not give you one and
Yeah.
eighth of a yard square.
And let's see. I just need a rough number. It just has to be. It only has to get the order of magnitude right. Doesn't have to be exact. So they only talk about
Probably have Antec, but more likely have
Okay. So we look at the die size. Okay, maybe this one. I think this one has a table of the die size.
I saw 26.
Sorry?
I saw
36?
26.
26?
Yeah.
Okay, well, that's fine. Okay. So we are looking at 160 versus 26 millimeter square. Big difference. Okay? But the bottom line is, is the energy efficiency. And RISC architecture is more efficient than CISC architecture. Now, why is that? I mean, if you look at the area, it doesn't really tell you the whole story. Because when you look at the area, you can say, oh, well, but since each instruction is doing more, it is okay to consume more energy. I mean, after all, it is getting more done. But when you look at the efficiency, it has to do with some transistors, basically wasting energy. Okay? Now, I can give you one single example to illustrate that one. Okay? Why do you think Linux is available to many, many architectures, but Windows is only limited to one or two usually? When they move on to a new one, they usually give up another one in terms of architectures. Why do you think that is the case?
It takes time to program for it.
Go ahead.
Programming time.
Programming time. Okay, so programming time is a very important bottom line when you are, when you write operating systems and you make money out of selling licenses of the operating system. But in Linux, you basically have quote unquote free labor, right? Graduate students, converting, porting Linux from one platform to another platform. But that's not the main reason, okay? Why do you think we have x86 instruction backward compatibility with the Intel line processor? Is it for the benefit of Linux? It's for the benefit of Microsoft. If Intel had a choice, Intel would have walked away from the backward compatibility baggage a long time ago, okay? Because in order to maintain backward compatibility, Intel had to sacrifice one, energy efficiency, okay? Because to emulate the instructions that your original IBM PC XT can execute is using up transistors, okay? And that is why, that is actually why a CISC architecture like the i5 processor is not energy efficient, because it's not spending all that silicon, all the transistors into actual computation. A lot of that is just to maintain backward compatibility. Is that,
Why do they
do you
have
guys,
to keep that,
sorry?
So why do they need to keep backward compatibility eventually?
Because as far as Microsoft is concerned, okay, now when you look at Microsoft as an entity, it only has so much resources. Okay, there's so many developers.
Yeah.
As much as Steve Ballmer keeps screaming, developers, there are only so many. I'm not going to show that video. I showed it once in my class, and that was interesting. Because later on in that class, one kid walked up to me and said, "Do you know what is my last name?" I said, "No, I don't really know." Ballmer. I'm a Ballmer. And he remember, Steve, the uncle, visiting him in Sacramento and stuff like that. That was interesting. What was even more interesting was at the end of the semester, the same person was asking me how to install Linux. No, that's not the weirdest part, okay? He was asking me how to install Linux on a PSP. Of all all platforms, okay? He was trying to install it onto a little laptop computer, which would be like, oh, here's a CD, do it. You know, he was trying to install it on the PCP, a PSP, sorry, a PlayStation Portable.
And is it feasible?
Yeah, it was interesting. It was the same semester when I think Windows 7 or I cannot remember, Vista or 7 was released. You know, one day he walked in with his friend and they were just waving their little shrink wrap package and go like, I got the first one. You know, it was funny. Okay, but getting back to the problem, you have a limited number of developers, okay, and so Microsoft can decide how to use all that developer power or energy, okay, or the resource. So it has several ways to make use of that resource. They can make their operating system more secure, okay. They can use it to make the new version of Windows look different from the previous one. Or they can spend the time to make the operating system less dependent on the actual architecture. Okay, you'll use abstraction and stuff like that, so that the assembly code that is actually architecture dependent is only about 5–10% of the entire code base. The rest will be written in C, C++, and it'll be very portable. Okay. Okay. What do you think is important to Microsoft?
Money.
It needs to make money, right? But how do you make money? If you make your operating system cross-platform better, is it going to help Microsoft make more money?
It must change the way it looks.
Exactly. That's the first priority, is to change Windows, then whatever next version is, so that it looks different from the previous one, so that people have a reason to update. Right? If Windows 10, Windows 8, I have to remember to skip 9, Windows 7, Vista, and they all look just like XP, the same old look with a start button and all the same, everything being the same. Nobody's going to upgrade. XP runs just fine with what, 1 gig of RAM? Why do I want to upgrade to something that needs 4 gigs of RAM just to load, right? So that's the reason. They have to spend the resources to make it look different. Next would be security, right? They have to address all the security issues because people were just pounding on Microsoft and saying, how come your operating system, has so much. Yeah, exactly.
Why does it suck so much?
And so they don't have energy left to really, make it cross-platform compatible. It's not like Linux where you have armies of graduate students doing it.
Yeah.
I mean, there are cases where Linux was ported to an architecture that was basically non-existent in silicon. It is still in simulation. So imagine this, okay? Imagine a super-duper version of this that is capable of simulating an entire new generation of processor. Okay, now very slowly, okay, but it will get it done. And the instruction set is released, the specification is released, and so on and so forth. They had people port who they can port Linux onto an architecture like that before silicon was even fabricated. Yep. So that basically tells you, the ability of people to port Linux into other platforms. But partially it has to do with the structure of Linux. It has a very small portion that is actually dependent on the assembly language part, and the rest are mostly just written in C and C++, which makes it highly portable to different platforms.
And that small part is the kernel? That small part of the kernel, or there's a small part of the
mostly
kernel?
in the kernel. Mostly it has to do with the multitasking part, and the other parts that has to deal with the actual processor. So
Then the productive part, but like you mean like the interrupts, so and those are much.
everything that has to do with interrupts, multi-threading, and stuff like that, all of that stuff need to be written in assembly because we're dealing with registers and other things that are very processor specific. All right. So are there any questions about the discussion today? But that really is one of the factors, okay? CISP versus RISC. RISC basically says, we push more of the responsibilities to the developers, people who write the program, software people. CISP, on the other hand, is taking more of the responsibility in hardware. We'll maintain backward compatibility so that we don't need to change compilers, okay? So that we'll keep using x86 tools as far as the Intel processors are concerned. RISC is saying, okay, here's the next generation. It's not going to be opcode compatible with the old one, and it will be up to the compiler people to retool the compiler, to retool the entire tool chain. It will be up to the programmers to make use of the new processor. But as far as the hardware, the die size is concerned, they can make it as small as they can.
So basically what you're saying is that if not for Windows, we could all be getting more bang out of our processors.
Oh yeah, definitely. There's really no doubt about it, and I'm not the only one saying it. Intel has been pushing it for years. Microsoft is the only reason that Intel is still making x86 backward compatible processors.
Not for Windows, you had
Yeah, that
machines that
might
did
suck.
an update and crash.
Sorry? But that was a comment. Okay. Because Intel wants to sell processors, right? It doesn't really care what operating system is being used, and the more processor they can sell, the better. So, if people use whatever processor that can sell well, they will say, okay, we'll make those. Intel actually fabricates ARM processors. In case you don't know, they do. They can license from ARM, which is a. Does anyone know who is ARM? Advanced RISC Machine. It's a British company, and it's an IP company. It's an intellectual property company. They do not make anything other than the design of the processor. And they license the design to manufacturers like Intel, Sharp, and a few other companies. I think Atmel is one of those companies too. And they will integrate the ARM processor into a chip, typically also with other stuff like LCD, circuitry and other things. Cell phones, it's the same way. Okay, who makes the cell phone processors? Qualcomm, right? And so the Qualcomm version of the processor basically has the ARM, usually, is it the 7 or the 9 series as a part of the core, but it will also integrate, cell phone specific circuitry onto the same die to improve the cost effectiveness of the hardware. So ARM basically just licenses the design and let people, let other people manufacture it. Okay, any other questions? No other questions? All right. So I didn't quite get to the file that I want to demonstrate, but so I will just go ahead and open it. Let you guys take a look at it for a few minutes, and I'll go to the lab and also. I'm not going to talk about class-specific stuff because not everybody can make it over there, and I cannot remember where I decompressed it. The text processor. No. Okay, so I'll zoom out. Okay, this is the design. Okay, so it doesn't look too bad, but when you look at some of these components, it is actually a component that I make. So when you look at registers, you can double click, and then you look at the component called registers. This is the inside of registers as a single unit. And then when you look at this part here, it is the ALU. So when you look at ALU, as a component, it looks like this. And this is a very, very simplistic processor. The only thing you can do is addition, subtraction, copy location of content from memory into register, and then copy the content of the register back into memory. So it's very, very simplistic. I'm still working on the microcode to make instructions. So basically, microcode is the subcomponent of instructions in order to exercise different portions of a processor to get something done that's specified by microcode. If you want to remember what microcoding is, you can have this mental picture. It's kind of like, how do you call those things you wind up and play music box? The mechanism inside the music box.
Turnkey, I think it was. Turnkey, I think it is. Turnkey.
It's the mechanism of a music box. So basically, when you wind it up and you let it go, it just has those little pegs that will basically tweak the times, yes, and it will make the sound. It's the same thing here. It's the microcode that is controlling which part of the processor to turn on, turn off, toggle this one, turn on that one, in order to actually execute instructions. Okay. So next time on Thursday, we'll definitely take a closer look at the processor. Okay, and what we'll do is we'll go from the inside out. We'll look at the very core of a processor, which is the part that actually does all the calculations. And then we'll take a look at the registers next, and then we'll take a look at the control circuit that makes everything possible. All right. I will go to the lab, in case anyone wants to go there and do the subtractor, homework assignment, which is actually somewhat trivial now that we know how to make an adder. Somewhat, yes. I guess I can.
Professor, sorry to state that. Is there
Yep.
any new homework assigned besides the subtractor?
Nope. There's no new homework assignment. Just the subtractor.
Yeah, subtractors do.